Here we go. Good afternoon. So homework is graded as promised. What I looked for was showing, number one, this small perturbation, showing that that's 0 due to steady state. Also the substitution, that was worth 1 point. And then showing products of small terms are small. That was worth 1 point. You had to show me the terms that you were knocking out, not just saying knocking out small terms. And then subtract steady state equation. That was worth 1 point. You needed to do more than just say that you did it. You needed to either list the equation or ID the terms. In other words, say these are the steady state terms, I'm subtracting the steady state equation out, or list the steady state equation. So those are the 4 steps to success: the substitution, knocking the steady state dots out, small perturbation assumption, and subtract. What's a subtract? Anybody have any idea? Subtract. All right, so ditto for number 2. Same 3 steps, same 3 points. So questions about those 2? That was fast, right? On the exam, there's likely to be a problem like this. Make sure you show me clearly all of the 4 steps, exactly like I've told you to tell me, and you'll be good. Okay, and then problem number 3. The cruise condition, we have an equation for CL, an equation for CM, an equation for CD. You look up the numbers that go into those equations. And then we solved for alpha, an elevator. So let's see, which solution is this? This is CL and CD. And we're looking for an angle of attack of 2.27, an elevator of 6.02. Those are in degrees. If you did it in radians, that was fine. And so that was worth 1 point there. And then the CL and CM, alpha and elevator, these are all steady state values. You should have gotten those values. And this was worth 1 point each here. And then the final question was worth the last point. And they're different, explain why they're different, and which one is right. So the explanation is 2-part. One, the drag model, we're using a linear approximation for the drag model, not a drag polar. So maybe that approximation is not as good. But the main reason is that angle of attack is pretty much correlated to lift, because angle of attack generates lift. An elevator controls pitch, so it's pretty much correlated to CM. And so that is another reason why this bottom solution is more correct. Some people noted that the elevator doesn't really affect this. CD delta E is 0. So that's another clue, is that the elevator doesn't change the drag. And so you're not picking the 2 best equations to solve for those 2 best unknowns. What we're really doing here is the trim problem, which is what we're going to start later today. Is Cm is equal to 0, Cl is equal to the weight divided by Q bar S. So the answer there was worth 1 point as well. Questions on that? Again, if you have questions, issues, complaints, compliments about how I graded your homework, they're always welcome in my office during office hours or via Zoom by appointment. Oh, let's see. So, reminder, exam 1 is next time, Thursday, in here, in person. So, exam 1, Thursday, what is it, September 17th? What's today, the 15th? It'll be the first 30 minutes. So show up on time because I will cut you off. We start at 4:10, so 4:40 we're done. And then we'll lecture for the rest of it. So it's tailored to be half of a normal exam in here. So it'll be half as long, probably even a little less. There will be part closed book and notes. And then there'll be a part that is open book, but no notes. So just the book. Yeah, for you guys that have electronic copies of the book, you'll need chapter 1 and then parts of chapter 3 that we've covered about the steady state forces and moments. And I told you which airplane you'll need. You will need airplane, I think it's G. Let me look in the book. No, it's airplane D. And so I'm talking about the appendix now, which you're familiar with because you just, the current homework has you looking at airplane A, right? Questions about the exam? I don't even know if I'd call it an exam. It's more like a quiz-am. No. Short answer, calculations, derivations. No demonstrations. You won't have to act out anything as a joke. As many as I can make up for 30 minutes. I mean, it's going to be less than 10 and more than 1. Yeah, it doesn't help much, but yeah, it's reasonable to complete it in a half an hour. Anything else?
Is it an online exam, but you'll be taking it here?
It's in person.
So,
That's why it's, well, so in person. I should write that, thanks. In John Bardo Center, 255. Should say live. So yeah. And
will you be writing
we,
everything on paper?
yes.
And submitting it to you?
It'll be a normal in-person, write on paper, pen and paper, use your calculator and your brain exam. Yeah, so there's nothing. I'll give you the piece of paper, you'll fill it out, give it back to me. There's no upload here to Blackboard or anything.
Do we have equations in?
On the open book part, no, because you have your book. On the closed book part, whatever you need, I'll give you. I mean, other than the answers to the questions. Yeah. Let's see, I'm going to do part on the board and then part on the touch screen. Let me look and see. Let's see, I think this intro to static stability I'm going to do on the board, and then we'll break it up by jumping to the laptop when we get into some of the equations, because I think they're a little clearer on that. All right, so a lot of what we're going to be talking about, we've already talked some when we talked through the different pieces and parts of the airplane, but I want to collect it all together in one place so that we can talk about it and see how it all fits together and make it easier to remember. All right, so the fundamental idea of static stability is that forces and moments are generated in response to a disturbance. And they're in a direction to oppose the disturbance. So the key words there are there's a disturbance. So maybe this is written a little backwards, but the first thing that happens is you have a disturbance. And in response to that, you get forces and moments. So part 2 is forces and moments are generated. And the key word here is they oppose the disturbance. So an example is there's an angle of attack disturbance that causes the airplane to pitch up. And you want a moment, pitching moment, generated to reduce that disturbance back down. It doesn't say the disturbance decreases, it just says that the moment is in the direction to make it decrease. So that's the key. And this is in relation to all of our steady state flight variables and perturbations on those. So let's list those. So the key thing is you always start out with an equilibrium, which we call steady state. Flight. So we say, okay, here's our forward velocity, our side velocity, our vertical velocity, P, Q, and R. So that's the steady state flight. Can you guys all the way over there see all the way down to there? I guess if you look at the screen, you can, right? All right, and then we have perturbations on that. These are the disturbances. And we say we have a little u, a little v, a little w, a lowercase p, q, and r. So if we're flying along at like 150 knots, something causes a gust in the forward direction. The airplane speeds up just a little bit for some reason. Forward velocity we leave alone. The side velocity we usually talk about as a perturbation in side slip. So instead of talking about v, we talk about a side slip, because side velocity is what generates the side slip. And then the vertical velocity generates an angle of attack disturbance. And in fact, we have talked about how the angle of attack steady state can be calculated from the tangent of those, and then beta is the inverse sine. Oh, sorry, this is W1 over U1 because it's tangent. So when we go through this, we'll talk about velocities, and we'll also say, well, it's really, we're talking about a beta or an alpha stability. Okay, before we start talking about the airplane, here's some real simple examples. You've seen these before because everybody draws these when you talk about stability. But it's worth doing because they illustrate the idea really well. Oh, I do need to make a comment. Notice that with the aircraft, there is no position stability. What does that mean? Here, the stability is all in terms of velocities, either angular or linear. And that's what the equations of motion are in terms of. There's nothing that causes an airplane, say, to always return to St. Louis. That would be kind of silly, wouldn't it? So the stability here we're talking about is stability with respect to these motion variables. And so the equilibrium is in terms of those. The simple example is actually in terms of position stability, because now we're talking about a marble in a trough, and the equilibrium in a trough or a bowl, the equilibrium is the marble in the bottom, and the position disturbance is up here. So here's the equilibrium, and here's disturbed. And obviously gravity generates a component of force, right? You have your normal force, and gravity is not directly opposing the normal force, so you get a component of gravity to return it back to equilibrium. Doesn't say anything about whether it actually goes back to equilibrium or not. And so this is stable. And then if you look at the opposite case, if you put the marble right on the top, you have equilibrium. But obviously, if you disturb it, the force generated actually moves the marble away from the equilibrium. So this is unstable. And then if you have the in-between case, you have a marble on a flat surface. If you disturb it over here, it just stays there. And we call this neutrally stable, because it doesn't move back toward the equilibrium. It doesn't have a force generated to go back, but it doesn't go away either. So it's in between. Another example that I know you've studied before is a mass spring system. And I'm deliberately leaving out the damper because it's not really related to static stability. So a mass spring, I said I was leaving out damper, cross that off. So here we've got a wall and a spring, big old chunk of lead here, and we want to track the X position of this. And so if we disturb this from this unstretched equilibrium, and this is easy to picture in your mind, right? Because we've all played around with masses and springs in one fashion or another. If you drive a car, you have a mass on a suspension spring. So the spring is unstretched, the mass stays there. If we pull it out to a new position, the spring is stretched. And the way a spring works is it generates a force to pull this back. So that thing is stable, statically stable. Again, equilibrium, perturbation, force or moment generated to move it in the direction to move it back to equilibrium. So if you keep that in your mind, you will have no question about any of the definitions or signs of stability derivatives as long as you know how the aerodynamics work on the airplane. So the question that comes up here is, so you pull this over to here and then you let go of it. Static stability says we're going to return back, but we don't know anything about how it returns. So the motion of returning is not static stability. In other words, does it go back to equilibrium? Right now, we don't care. And this would be dynamic stability. Depending on what you want from this thing, maybe you want the mass to go back and forth and oscillate for a really long time, right? If this is the suspension system in your car and you hit a big pothole, you probably don't want your car to bounce up and down for the next half mile down the road because the suspension, you want some kind of damping, something else in there to damp out the motion. In fact, that's the damper or the shock absorber, right? So if you have a car with really bad shock absorbers or no shock absorbers, it will bounce up and down. And if you have a really, really stiff spring so that it won't allow the tire to move much, then you have a really stiff suspension and the bumps you really feel when you hit them. But that's not static stability, that's dynamics and what happens afterwards. All right, so I want to pull up a scan from a page in your book. If you have your book with you, this is on page 187. All right, I'd get it rotated before I shared it. All right, so in this table on the top, they're showing the motion variables that we talked about. These are the perturbed motion variables. So there's U, V, and W. Here's P, Q, and R. And then here's the derived variables that we talked about, the perturbation, side slip, and angle of attack. And the way you read this is going down underneath, let's say, beta. This grid here is the force or the moment that's generated to oppose beta. And we've talked about both of these, CL beta and CN beta, but we'll go through those in more detail. But so there is a rolling moment and a yawing moment generated that oppose those two disturbances, or that beta disturbance. And so if you look at a different variable like W, we look down here and it says, okay, there's a Z force generated to oppose W. We're going to go through each of those entries in this table individually and explain them. So that's what we're going to do probably with the rest of the class today. We may get started on trim. I don't know. We'll find out. All right. So I lost my screen here. Okay, we're set up now. So this is static stability criteria. And the starting point is that velocity perturbations, U, V, and W, are opposed by forces. That makes sense because if you want to change a velocity, you apply a force. That's just Newton's law. And then the second key feature is that angular velocity disturbances, P, Q, and R, are opposed by moments. Because a moment creates an angle, an angular velocity. And then there's a few that don't fit into that kind of normal scheme. These are the angles, so alpha and beta, because they're angles, so they're opposed by moments as well. And that makes sense because an angle can get changed by a moment or a rotation. So we're going to just walk through each one of these. So we're going to talk about the perturbation on the forward velocity. So according to the rules listed above, this is number one, so U is going to be opposed by a force in the same direction, x, and since u is forward, we need to have a backward force. And the idea is this is going to reduce u back to 0. So we get u, the airplane's going forward faster than the steady state, so we want to force backward to oppose that. And so what this means in terms of a derivative is the derivative of the total x force has to be negative. It's going to move from 0 in this trimmed steady state case to being negative. But aerodynamically, we talk about the x aerodynamic force as being in terms of the negative drag, and then the thrust coefficient so we're talking about how does the drag change with forward velocity? How does the thrust change with forward velocity? And the tricky part about this is that dynamic pressure also has u in it, as well as the drag is going to change with u. So if we're going to write this out fully, we have to use the product rule on this. So by the subscript u, we mean this is the derivative of CD with respect to u. And then we have to have the other part of the product. So that was the derivative of the first part. This is the derivative of the second part. And dynamic pressure obviously depends upon u, so that makes sense. But then we look at this. So far, so good. I want to make sure I'm going to go through this slowly, and then all of the other derivations look exactly the same. So, but I want to go through this. So we write the force of the moment in terms of its coefficients, and then we realize, well, Q also changes. But if we look at this, typically in cruise, the thrust equals the drag in any kind of steady state flight. So in fact, this is going to be canceled out because the thrust equals the drag. And this is usually a small effect anyway. So 0 times small gives 0. And so what we're left with is this term here. And that gives us our stability criteria. Mainly focused on this one, because this effect is not real big. The thrust doesn't change a whole lot with a small perturbation, but the drag can. So this says that CD subscript U, notice the negative sign, so we have to flip this sign. And we get to this point, and you go, well, yeah, that's obvious, right? If the airplane speeds up, we want the drag to increase. And that is a force opposing that forward speed disturbance. So the second thing we look at is a side velocity disturbance. And here we want this to be opposed by a negative side force. And so we write the same equation, the change in the total side force with respect to a side velocity. And then we chain rule it, do it in terms of the side force coefficient. Like I said, I did the first one in detail. This one I'm going to shortcut. Really, we're saying, well, the thrust doesn't change much with side velocity. In fact, there's usually not much thrust in the y direction, the sideways direction anyway. This is a crappy CY. And here, again, the dynamic pressure doesn't change much with side velocity. So we get the derivative of CY, the coefficient with respect to side velocity. But if you remember, side velocity is proportional to beta. So typically we write this as CY beta. And as you can imagine, the W stability is going to look a lot like this. All we do is replace V's with W's. So have I gotten too far ahead of you? Let me know. Can I scroll up? Everybody good? So the last one is we have a vertical velocity disturbance, and so W is going to be opposed by a Z force. So it's just FZ. It's going to be in the negative direction because we want the force to oppose the disturbance. So the formula is going to look exactly the same, except now we're talking about the Z direction and a W disturbance. So the change in the force should be less than 0. Yeah, let me make sure I had this right. Yeah, I don't know what I did here. This is a mistake here. No, that's correct. It needs to be negative. So all of these, this is less than 0, so that makes it negative. My brain had a mental fart there. We're going to say the thrust in the Z direction is small. And so really we get a derivative with respect to W of the lift coefficient. And lift is in the negative Z direction, so we put a minus sign there. And that gives us our stability criteria. Of CL subscript W has to be greater than 0, less than 0, but W is directly related to alpha. And so this says CL alpha has to be greater than 0. All right, so the three stability criteria that come out of this are this. CL alpha is greater than 0. Most airplanes, that's just normal, right? Your wing is designed so that if you increase the angle of attack, you get more lift. So almost all airplanes are good with respect to this, unless we're stalled. Because if you're stalled, increasing the angle of attack actually reduces the lift. So that's the first indication of many that we'll talk about during the semester. That is, when an aircraft is stalled, a lot of the stability either goes away or flips sign. And that's what causes spins and all the problems with stall. Okay, I have a question for you. So there's the CL alpha. CL alpha has to be greater than 0. I got this backwards. This should be negative. This says, because if you look at this is less than, this is CY, so this is CY beta is less than 0. Good thing I caught that. And this says CDU has to be greater than 0. So why is that one greater than 0? This one less than 0? And this one greater than 0? Because they're all, one of them is related to U, one's related to V, and one's related to W. Any ideas? Anybody have any idea what I'm saying? So this is greater, this is less, and this is greater. So what caused the flip in the sign in these two is that the drag is in the negative x direction and the lift is in the negative z direction, but the side force is in the positive y direction. So it's just the definition of CL and CD as being in the negative x and z directions that causes that flip in sign. I wanted to mention that because if you're looking at that table that we looked at earlier, you go, well, why is the sign, the less than or equal sign, different on two of them? Kind of what? You mean down like that?
Yeah, down
There we go.
to the Y.
Yeah, I apologize. This should be CY beta less than 0.
So V is opposed by negative FY or?
They're all like U is opposed by negative FX, V is opposed by negative FY, W is opposed by negative FZ, but FZ is negative of the lift, so that's what flips it. And FX is negative of the drag, and so that's what flips that one. Let's see, we have 5 more of these to do. Let's take a break. Stand up, stretch, go get a drink of water. We're going to start back up here. If you have a question, ask it in front of the whole class unless it's specific to something. Sorry, what?
When you talk about the side of this, you ask why this,
Yeah.
this. Yeah, I couldn't hear it well, so I just want to ask you about this. And you say here you say is caused by the
That's because the lift is in the negative z direction and drag is in the negative x direction.
Oh, yeah.
All right, did everybody stand up and wake up? We'll do about 10 more minutes and we'll call it good. Is anybody still out? All right, let's do angular rate stability. These are easier. So here we're talking about a roll rate disturbance. And it's opposed by a moment in the opposite direction. So how does that work? The change in total rolling moment due to a P has got to be negative, less than 0, because that's going to reduce the angular rate. Again, we write this in terms of coefficients. Rolling moment coefficient, aerodynamic and thrust. And we say the thrust doesn't really produce much of a rolling moment. I told you these were easy, so we just get CLP is less than 0. So that means if the airplane starts to roll positive, right wing down, a moment is generated to oppose that, to roll right wing up. Same deal with pitch rate. So with pitch rate, if we have a disturbance, this is opposed by a negative pitching moment. And so this is easy to write out. Total pitching moment, how it changes with pitch rate, turn it into a coefficient. And we'll say that there's not a whole lot of pitching moment due to the thrust. At least it doesn't change much with pitch rate. And so you get that CMQ has to be negative. These are all easy to remember because this is negative because it opposes the disturbance. This is negative because it opposes the disturbance. And the same deal with yaw rate. So the total yawing moment changing with yaw rate, turning it into a coefficient. We say that there's not a whole lot of change in yaw rate due to pitch rate and the propulsion direction. So again, Cn subscript R has to be negative. So if the airplane starts to yaw nose right, there's a yawing moment in the negative direction to stop that. And then we have the angular stability, the alpha and beta. How are they opposed? And so if we have an alpha disturbance, it's opposed by a negative pitching moment. And we know that Cm alpha has to be negative, but it comes from this direct definition. An angle is opposed by a negative moment. So the total pitching moment. And notice in all of these, we're assuming that the angle of attack doesn't change the dynamic pressure. And the ones above here, whatever the variable is, doesn't change the dynamic pressure like we had in those velocity ones, because the velocities are directly in dynamic pressure. And so again, we say, well, alpha doesn't change the pitching moment due to thrust very much. And so here we get Cm subscript alpha, which just means the derivative of Cm with respect to alpha has to be negative. So again, you can memorize Cm alpha as negative, but fundamentally, if you get a positive alpha gust, you want to pitch back down into the gust to reduce it. And then how about beta? It's the same story with beta. You can kind of see how if you've done one of these, you've done them all, right? And that's because the fundamental concept is equilibrium plus disturbance creates something that returns the disturbance back to where it came from, to zero. So here, beta is opposed by a positive yaw. Why is that? Beta is defined as coming in from the right side of the airplane. Positive yaw gets rid of that beta. Why is this negative? You should always ask these kind of questions. If one's positive and one's negative, you should say why. And it's because how alpha is defined is the wind coming up from the bottom of the airplane. And so to reduce that, we have to pitch in the negative direction. So really, it just has to do with the definition of alpha and the definition of beta. If we said positive beta was the wind coming in from the left, then it would need to be opposed by a negative yaw. But that wouldn't really fit with the side velocity because the y-axis is at the right side. And so that's why we define beta on that side. And the z-axis is down, so that's why we define alpha in that direction. If you write your own book or make your own calculations, you're welcome to use any convention you want. If you change from the normal convention, expect people to be confused or even worse, angry, because you're changing how they do stuff and it makes it hard to keep track of, right? You guys remember in 514, right, the aileron convention in Etkin was the opposite of in this book here, Roscom, and that's confusing. Anybody here driven in a country where you drive on the left side of the road? That's fun. Maybe for you, you come from that country and then coming over here, it was crazy, right? I drove in Australia and we wanted to make sure that we didn't die, so we had 3 people in the car watching traffic and making sure the driver was on the correct side of the road. But then what was weird is we were over there for 2 weeks and we came back here and got in our van at the airport and we're driving down Kellogg and I was like, this feels weird. And it was because we were on the right side of the road. So you get used to it. The brain is incredibly adaptable. All right, how about this? Beta is opposed by positive N. So now we've got an opposite less than or equal or greater than sign just because of that. Totally because that's how beta is defined. And so this simply says that Cn beta is positive. And we've talked about this already. What you want to do is yaw into the side slip. And in fact, in the pitching moment, you pitch into the alpha. It's just that alpha is below rather than above. All of this goes back to you want to change, you create a force or a moment to oppose the disturbance. All right, so that's the end of the normal derivatives that we talked about. Forces, velocity disturbances are opposed by forces. Angular velocity disturbances are opposed by moments, and then alpha and beta are opposed by moments in the same direction or same axis. So there are two oddball derivatives. Because they don't fit into that kind of normal definition. And these are oddball because they really have to do with gravity effects. And one of those we've already talked about with respect to gravity is that beta disturbance is opposed by a negative rolling moment. And that doesn't fit very many of the definitions because beta is a disturbance about the z-axis, a rotation, but L is about the x-axis. But we've described that as bank angle stability. So if you have your airplane, it's flying along straight and level, and it banks like that to the right, then gravity is going to cause the airplane to slide sideways, which produces a relative wind coming in, or it produces a positive beta. Right, airplane moving to the right, beta is coming in, the relative wind's coming in from the right. That produces a positive beta, and because we want this thing to roll back upright, we want that negative L. So in terms of a coefficient, I don't need to write because we've done so many of those. We want CL beta to be negative. And the explanation is that if the airplane banks to the right, it's going to start side slipping to the right, and we want it to roll back upright. You can say it rolls away from the side slip. But that seems kind of backwards because you would usually roll or bank or yaw into something to reduce it. But in this case, it is really the bank angle disturbance, not so much the beta that comes from it. So that's why I call these gravity effects. And then here's the last one, and then we're good to go. They talk about, in that table, a forward velocity disturbance opposed by a positive pitch rate or pitch moment. And that's totally bizarre because that's a velocity that's opposed by a moment, not inside the rules that we've defined. But again, this is a gravity effect. And it's because if you have an airplane and it's flying along straight and level, and it starts to go faster. So we have the forward velocity, and then we have some extra forward velocity. The way to slow the airplane down is to pitch it up, because gravity is then going to be acting partially backward to slow the airplane down. So that's why I call it a gravity effect, is that if you pitch the airplane up with a positive pitching moment, then eventually velocity will decrease back down. In fact, pilots use this to control their velocity. They will point the nose down if they want to speed up quickly, and they'll pitch up to slow down. They won't mess with the throttle so much unless they need to make long-term changes. And so this simply says that CMU needs to be positive. We want to pitch up to slow the airplane down. And this is an important Mach number effect, actually. So this is not such a big deal at low speeds, but if you get up at the high speeds, they've discovered that sometimes when you're close to Mach 1 over the airfoil or over the wing, small changes in velocity change the shock wave pattern and can actually cause the airplane to pitch down, and it goes faster. And so you get more shock waves, and then it pitches down even more, and you go faster, and it sounds great except when you hit the ground. Okay, that's it for today. Any last minute questions about the exam? The general format of it, what's going to happen? Yeah. I'm going to walk over there so I can hear better. Yeah. The homework and the reading in the book, because it's some of it will be homework problems and some of it is general concepts. And like the derivations we've done in class. Make sure you go over those. All right, let's go home unless you have another class. Oh, big news. Did you hear it? Well, they were using, gosh, I forget what kind of telescopes. They were studying the atmosphere of Venus, and they discovered a certain, actually it's a toxin in the atmosphere, but the toxin only occurs when life is there. In fact, it said we have it in our intestines, but it's a toxic substance that almost always, at least on the Earth, only occurs when there's life. So now everybody's excited and they want to send a probe to Venus for good reason to find out whether there's actually life in the atmosphere or not. It's cloudy there, so there could be cities underneath the atmosphere, right? Probably not. I mean, it's a highly corrosive atmosphere and it's really hot. So if there's life there, it's going to be scary. Yeah. You have a question about your homework?
The one you just graded?
Yeah. Okay. Let me shut this down. Any other general questions? Anybody want to go to Venus? You do? I'm watching a show, maybe I mentioned it, it's called Away on Netflix, about a mission to Mars. It's kind of fun, except it really gets into, it's almost like a soap opera about the people and how they interact, which is part of the deal. But I'm bugged by the fact that there's a team of international people that are going to Mars together, and they've been training for a year, and they're squabbling and fighting each other, which, you know, that would never happen. If this team trained for a year, they would have figured out who didn't like who and fixed it. But anyway, you would hope.